forecasting model that is a limited area model, in particular applying the 3D var and 4D var variational assimilation techniques implemented within this model. The observation come from the meteorological airdrome reports, mainly issued by the Italian airports, from the regional agencies for the protection of the environment existing in every Italian region, and from Meteo Network, a no-profit organization which collects many stations, especially in northern Italy. Specifically, the assimilated observations are surface temperature, dew point temperature, pressure, and wind velocity and direction. But what is the variational method for data assimilation? The variational problem consists in finding an optimal initial state at the start time for the forecast, let's call it T0, minimizing a scalar function, the so-called cost function, which considers firstly the observations to be assimilated. However, this observation information needs to be transported on the model grid points on which the physical equations are solved. So it's necessary to have a background field to relax this information. A background field that is typically a different forecast coming, for example, from a global model that is valid at the start time T0 and is interpolated on the model grid. In particular, 3D var consists in assimilating the data only at one time instant. 4D var solves the same variational problem of 3D var, but it allows to increase the time window of data assimilation, considering multiple time instants. And in this technique, also model equations play a role in providing the updated initial state. So due to these features, this technique is more computationally expensive than 3D var, and this is taken into account in the study in terms of the computational time. In the study, meteorological data come from the Global Forecast System, GFS. They have their own resolution, so they are interpolated on the WRF model grid. This interpolation provides the initialization file, which represents the initial state of the atmosphere from which a forecast without data assimilation can be executed. However, the same initialization file can also be considered as the background field for the WRF data assimilation system. So the system takes into account the background field and its associated properly computed accuracy information and the observations that are simulated. Observations that undergo an elaborated pre-processing phase in which they are fit for the introduction in the model. So the minimization algorithms work to provide the updated initial state from which a forecast now enriched with the information coming from the assimilated observations can be executed. Finally, a comparison between these two kinds of forecast valid at the same time can be executed to see if there are any improvements brought by the assimilation of the observations. The model horizontal resolution is set to 4 kilometers, and the contour meteorological GFS data that are interpolated on this model grid have an initial resolution of 25 kilometers. For what concern the convective processes, a cumulus scheme is used, and for what concern the other physical processes, for example, microphysics or physics of the boundary layer, and etc., the WRF default operational schemes are used. So let's start from the first event, the 14th of June. From the synoptic reconstruction using GFS data at a quarter of the Brio resolution, we can see in the late afternoon a cyclonic circulation with a thickness minimum located on the Adriatic Sea, which, as you can see from the wind field at 500 hectopascal, moves here from northeast above the investigated region, Lombardy. The relative humidity field at 850 hectopascal reports larger values of relative humidity in the northeast and beyond the Alps. So if we look at the radar images, we can see a relatively calm situation in the early afternoon. Then some precipitation affected the eastern areas in the late afternoon, and at around 20 o'clock, two storm nuclei generated and close to the Lake of Como, and then moved together, affecting the area of Milan in the evening. On the right, you can see the hourly rainfall images provided by the WRF forecast without this assimilation. They reveal a model able to capture the precipitation on the eastern areas and also a principle of precipitation close to the Lake of Como. But then the model sees no further development southwards. So here's the problem for the first event. For the second event, we have in the early afternoon trough approaching the Alps and so causing disturbances also in northern Italy. The wind field at 500 hectopascal reports wind directed eastward above the region, and the relative humidity at 850 hectopascal reports larger values of relative humidity in the northeast and lower values, in particular at the border between the two regions, Piedmont and on the left and Lombardy to the right. So if we look now at the radar images, we can see in the early afternoon that sorry. Okay, in the early afternoon, suddenly a storm front takes place between the two regions. Then this storm front rapidly moves eastward and leaves the region in the late afternoon. The model, without assimilating any data, is not able to capture any convection triggering between at the border between these two regions. So here is the problem for this second event. So moving back to the first event, all the surface observations available at 14 and 15 o'clock are assimilated, and both 3D VAR and 4D VAR techniques can be applied. If we look at the forecast using the 4D VAR techniques, so assimilating all the data available both at 14 and 15 o'clock, we can see that now the model is able to capture also the generation of the two storm nuclei close to the Lake of Como and the subsequent movement southwards, similarly to what we observed from the radar, even though the model is anticipating the event by 1-2 hours. Anyway, it is an improvement compared to the prediction of the model without data simulation. For the second event, the same approach is applied, so all the surface observations available at 14 and at 11 and 12 o'clock are assimilated. But in this case, neither 3D VAR nor 4D VAR techniques were able to improve the forecast. It appears like the information coming from these assimilated surface observations is not able to improve to correct the inaccuracies existing in the initial state of the atmosphere enough to allow the model to predict the event. So we decided to look at the upper level information. On the left, you can see the relative humidity profile reported by the radio sending of Milan in blue at 2 a.m. and in orange at 2 p.m. So you can see that in 12 hours, there is a decisive increase of relative humidity in the lower levels. Looking on the right at the relative humidity profile predicted by the WRF model at 2 p.m. Without assimilating any data in orange, assimilating all the data available at 12 in green, and assimilating all the data available both at 11 and 12 in red, you can see that generally the model underestimates relative humidity both at the lower levels, so at 900 and 800 hectopascals, but also at the upper levels, so at 600 and 500 hectopascals, where in blue, the radio sounding reports values close to 100%. The radio sounding of Milan is the closest radio sounding to the area where we observe the convection triggering, so at the border between the two regions. And it's not so far. So it's reasonable to assume that this underestimation of relative humidity was existing in that area also at 11 and 12 o'clock. So also thinking at the future possibilities to have hourly available satellite data to an additional vertical sounding, we decided we supposed to have about 70 virtual soundings spaced 10 kilometers between each others and located in this area. Each of these virtual sounding is supposed to report at 11 and 12 o'clock relative humidity values close to 100% at these 4 pressure levels. So this upper level information is added to the already assimilated surface information. And the results show in particular that the model is very sensitive to the addition of this upper level information about relative humidity at 900 and 800 hectopascals, so at the lower levels. In fact, if we look at the forecast using 4D bar techniques, so adding this information of relative humidity, it's possible to see that now the model is able to capture the convection triggering, the capture of convection triggering at the border between the two regions and the subsequent movement eastward of the storm front, similarly to what we observed from the radar. So, summarizing from the first event, we can observe that 3D bar and especially 4D bar were able to improve the forecast from an operative meteorology perspective because the correction of the initial state of the atmosphere leads to a prediction that even if it's not perfect in terms of time or quantities, allows to have a different awareness of the imminent worsening of the weather conditions compared to the prediction without assimilating any data. From the second event, however, we can also observe that sometimes the surface information can be not sufficient to allow the model to predict the event. So upper level information reveals decisive, essential sometimes. And so thinking about the future possibilities, it would be interesting to use hourly available satellite data for improve the 3D structure of the atmosphere at the start time for the forecast, but also would be interesting to use other further data, for example, radar reflectivity data or lightning's data. So all these kind of sources can work together to improve the modeled initial state of the atmosphere, and so improve the prediction for nowcasting and why not also for short-term forecast. And on a final aspect, interesting aspect would be to have a convection permitting model. So in this study, we used a resolution of 4 kilometers. So we decided to use a cumulus scheme to parameterize the subgrid convective processes, but letting the model explicitly solve convection will certainly be an advantage, because a convective scheme is another source of errors anyway. So yes, that's it. Thank you for the attention.
Thank you, Michele.
I don't know if I have to.
Yes, you can share still the screen just in case.
Yes.
Yes. Now I open the floor to the discussion. Questions from the committee?
Yes, I have a couple of questions.
Yes.
Compliments for your presentation, and thank you for the presentation. I have first a curiosity. I was wondering why you choose those two data of last year weather. Why particularly those two?
Yes, because we were studying I started the thesis in March, so we decided to look for actual recent events because yes, was interesting to to study something that was just happened, but there is not.
It's not a scientific reason.
No, yes, the reason was that they were interesting because the forecast were missing some information, and so there were some damages for some cities. So it was interesting to see if there with the help of data assimilation, this problem could have been resolved. So yes, this was the main reason.
I see. And the other question is, you showed the radar image and the forecast. I'm not an expert of meteorological models, so I mean, how can you say if the model is capturing the ground truth, which is represented by the radar? Is it based on observation on the ground? Is it based on, is there any statistical or analytical method to say if the precision was correct?
Okay, so the radar images are reflectivity data images. And so on the left, the forecast is, we are looking at hourly rainfall images. In the study, we used also some stations, HARPA stations, to compare the quantities reported by these stations to the hourly amounts of rainfall predicted by the model. So yes, there is also a quantitative analysis in the study. And in this study, in this analysis, the model reveals often to overestimate the rainfall amounts, especially in some areas. And so yes, we did a comparison between these two kinds of rainfall amounts data.
I see. Thanks.
You're welcome.
Thank you. Other questions from other committee members?
Maybe I have a question.
Yes.
Yeah, I think it's sometime connected to the discussion that you made at the end about the Cumulus module and the use of a higher resolution. But which is the effect of the start time of the simulation? I mean, you probably start at some time because you had some data to assimilate at that time. But is there a strong effect, for instance, by starting some hours before or later if you have other data?
Yes.
Because somehow, I mean, just to conclude, I mean, somehow maybe there are some processes that are better resolved in the high resolution model that can compensate for the absence of information at some time. And so if you start with the high resolution model before, maybe you can capture them.
Yes, the hour it's not. It depends on the events. I think it's not easy to understand when. I mean, there is not a general rule to understand where you can start to assimilate data for improving the event. Maybe I didn't get the question well, so I
mean, you didn't try to see what happened when you started the simulation at a different time.
Yes. For example, for the first event, yes, we looked also at what happened if we assimilated 2 hours before, so, or 3 hours before. And yes, there are some window of assimilation in which the forecast doesn't improve. Yeah, the model doesn't improve the forecast, but other window of assimilation in which the forecast is improved. So yes. Before, so for example, for the first event, we assimilated at 14 and 15 o'clock. But we also assimilated previously, so for example, at 12 and 13 o'clock. And in that case, there wasn't an improvement in the forecast. So we decided to continue assimilating at 14 and 15 o'clock. But the problem was also that 4D VAR technique was very computationally expensive. So we used only a time window of assimilation of two hours. but it would be interesting to increase also this time window of assimilation and having also a moving time window. So to consider also a time window of 5-6 hours. And yes, sometimes you can improve the forecast using a different time window, as sometimes was not possible. So yes.
Okay, thank you.
Okay, thank you. I think we have time for just one or two quick questions.
I also can ask.
Please, Daniela. Yes.
Then a question. You showed us the data that were coming from the weather stations, and there were quite a lot of weather stations in the interval. The slides with the points where the data were coming from.
Yes.
Yes, this one. I was wondering whether have you tried to see what happens if I'm not using all the data, but I don't know, half of the data to understand whether it's important to have all the data coming from all the stations, or I could still do a forecast with just picking out a few points.
Yes, we at the beginning for the first event, we try to use only Meteor network stations existing in only in the region of Lombardy, for example. And for the first event, the forecast was improved. I mean, the two storm nuclei were predicted also in that case. The difference using also the other data was especially an increase in the amount of rainfall predicted. We noticed this as difference. But yes, for that event, also assimilating the data coming from the Meteor network station in Lombardy was useful.
Okay, thank you.
Michele, Daniela, are you okay with this reply?
Yes.
Okay.
Thank you.
You're welcome. Thank you.
I have one question. You have become confident with this model in the end, I guess, after using it in a few ways. But I think that there might be something you would like to explore more. So should you have the opportunity to go on with your research, which steps would you make? Which aspects of the performance of WRF would you like to explore in connection to data assimilation?
Which aspect of the WRF model?
Yes, or the WRF suite, in which configuration you would like to explore?
I would like to know better the various microphysical or the other physical schemes. Yes, because there are many schemes used that can be used in the model, and so it would be interesting to catch the differences. But yes, I would like to have a more powerful computer to also increase the time window of assimilation, because I think that it would be very helpful. And yes, also to increase the model resolution of the model, to let the model explicitly solve convection, because in that case also orography can be improved a lot. So yes.
Thank you. So unless there are other questions from the committee, I think we should move on. And so thank you to the candidate. And I kindly ask Selene to set the student, the candidates, and those who are not part of the committee in the lobby, in the waiting room.
Okay, and I stop the live stream.
Thank you, Tiziano. Please give us your presentation. We have 15 minutes.
Thank you. Good afternoon. The topic of my master thesis is analysis of micrometeorological processes in an apple orchard in the Adige Valley, Italian Alps during late frost events. So late frost events occurring from the late winter to the early spring can cause several damages to crops, in particular vineyards and apple orchards. For example, in Trentino, 140 million euros were refunded to farmers in 2017 due to several late frost events. So in order to mitigate such events, there are different types of protection systems, like heaters, wind machines in the pictures that mix the air inside the canopy, and overhead sprinklers, the most widespread method, in order to protect orchards from very low air temperatures. So my thesis is based on data collected by the GEPRI project, Gelate Primaverili, Spring Frosts, and the study area was Maso delle Parte, an agricultural farm in the Piana Rotagliana, 15 kilometers north of the city of Trento. Measurement campaigns were carried out from March 20 to May 13, 2003, and from December 4, 2003 to May 10, 2003. Aims of the project and of my thesis are the identification of main physical processes, the quantification of energy balance components, the investigation of air temperature profile near the ground, and evaluation of wind-induced effects. The following instruments have been installed within a row of an apple orchard. Top left, a last weather station for air temperature, wind speed and direction, and relative humidity measurement 3 meters above ground level, and 8 thermocouples on a support rod for air temperature measurement from ground level to 5 meters above ground level. In the center, 6.5 meters above ground level, ultrasonic anemometer gill for wind speed and direction measurement, and a gas analyzer Lycor for water vapor measurement. Bottom left, a net radiometer for incoming and outgoing radiation measurement, 2 meters above ground level. And at the center, a sonar for vertical profiles of wind speed and direction up to 800 meters above ground level. Bottom right, a soil heat flux sensor 1 centimeter below the surface, and the first sensors at different depths for temperature profile in the soil. So I analyzed 2 different types of frost events. The first one occurred on February 24, 25, 2004, and all the following charts consider a 24-hour time window. In this case, from midday on February 24 to midday on February 25. So synoptic conditions. Top left, the geopotential map at 500 hectopascal at 0 UTC on February 25, where a low pressure system with a minimum of 985 hectopascal is present on Scandinavia, which brings colder air over Europe. Bottom left, the geopotential and temperature map at 850 hectopascal with the cold air advection over Europe. Top right, the windrows 3 meters above ground level with the wind from northeast. And bottom right, the windrows 6.5 meters above ground level with the wind from the north. So evolution of air temperature was measured by the 8 thermocouples at different levels and wind speed 6.5 meters above ground level. So after sunset, here, the temperature drop is divided into 2 main phases. During phase 1, the decrease is linear until 6 p.m., this line, when thermal inversion near the ground starts to develop with colder and heavier air near the ground. In phase 2, from 6 p.m. until sunrise, the decrease in temperature is influenced by Föhn wind gusts. So, so in the two boxes, the blue one during the evening and the red one during the night, in the presence of wind, the air temperature fluctuations can be seen, the blue arrow and the red arrow. So an increase in wind intensity corresponds to an increase in temperature and vice versa. So here the evolution of air temperature profiles range from midday on February 24, this line, to 6 a.m. on February 25, the yellow line. The apple trees have an average height of 2.5 meters here, and the base of the branches is alpha meter high, as in the picture. At midday, this line, the profile is homothermic. Then, only after sunset at near 4 p.m., the thermal inversion near the ground starts to develop, with higher difference here during the evening. At midnight, this line, the temperature 1 meter above ground level is positive, while the temperature below 1 meter is negative. Then during the night, the other lines, the profile becomes more linear with negative value temperatures at all levels. The relative humidity was measured 3 meters above ground level, and is low because of the north wind that advected dry air into the Adige Valley. The lowest value, around 30%, is measured at sunset. Then relative humidity starts to increase during the evening and the night. So in this case, as for air temperature, relative humidity is affected by the presence of wind, which causes a slight drop in humidity during the evening in the blue box here, and during the night in the red box. Finally, cumulative energy fluxes were evaluated. The cumulative energy fluxes correspond to the integral of the energy fluxes over time in the 24-hour time window from midday to midday. And the cumulative latent efflux, the blue line, and net radiation, the yellow line, are the main heat loss factors due to the presence of dry air, which enhanced the evaporation, and clear sky condition. The cumulative ground heat flux, the green line, is positive after 6 p.m. So the ground releases heat towards the atmosphere, and the cumulative sensible heat flux, the red line, is negative, so after 6 p.m. Then the second frost event occurred on March 28, 29, 2004. Like before, all the following charts consider a 24-hour time window. In this case, from midday on March 28 to midday on March 29. So synoptic condition. On top left, the geopotential map at 500 hectopascal with a high pressure system here over North Italy of 1020 hectopascal is present, providing clear skies and stable condition. Bottom left, the 850 hectopascal geopotential map with cold air that is confined to the north of the alpine chain. Top right, the windrows 3 meters above ground level with prevailing southwesterly winds. And bottom right, the windrows 6.5 meters above ground level with prevailing winds from southwest during daytime and a small wind component from the northeast during nighttime. So these windrows shows the presence of breezes along the Adige Valley. Okay, so like before, the evolution of air temperature. And the temperature drop is divided in this case in 4 phases. During phase 1, like before, the drop is linear, and the drop is linear, and where the heavier and colder air is near the ground. In phase 2, from 6 p.m. until 8 p.m., the decrease is influenced by the up valley winds from the south with an average velocity of 3 meters per second. Then the most interesting phase is the phase number 3, from 8 p.m. to 11 p.m., where temperatures are quite constant, and in particular at the higher layers, for example, the chan line 3.2 meters above ground level and the red line 5 meters above ground level, there is a slight increase in temperature. So this is caused by the Hora del Garda wind in the red box during the evening from southwest that blows up the Lakes Valley and flows into the Adige Valley north of Trento, carrying warmer air. Then at 11 p.m., Hora del Garda wind stops, and in this point there is a sharp decrease in temperature, in particular at the higher levels. Then the last phase, the phase number 4, where temperature drops more slowly until sunrise, where negative values are reached only in the first meters above the ground. So evolution of air temperature profiles from midday on March 28 to 6 a.m., the yellow line on March 29. At midday, the ground here is quite warmer than the atmosphere. And like before, after sunset, the thermal inversion near the ground starts to develop. An interesting thing is that the profiles at 8 p.m. here and 10 p.m. are very similar, and this is a clear sign of the Hora del Garda wind presence. Then after midnight, temperature drops linearly at all levels, reaching minimum values a few tens of centimeters above the ground. So the only exception is the temperature near the ground measured by the thermocouple at 0 meter, which is influenced by the presence of the grass and the ground itself. Then, as for air temperature, relative humidity is affected by Hora del Garda wind that mix the air layers inside the canopy of the apple orchard. So in this case, in the red box, the relative humidity is quite constant between 8 p.m. and 10 p.m., corresponding to Hora del Garda actions. After this phase, the relative humidity rises again, reaching values close 100% during the night and during the morning. Finally, cumulative energy fluxes with, in this case, latent heat flux, blue line, and sensible heat flux, the red line, that are quite constant after sunset. So therefore do not contribute to heat loss towards the atmosphere, like the cumulative ground heat flux, the green line, which at the end of the 24-hour time window is 0. So in this case, net radiation, yellow line, is the main heat loss factor from sunset to sunrise due to the presence of clear sky condition and calm wind condition after 11 p.m. Then a simple cooling model, the Reuter model, was applied to reproduce ground temperature during the 2 frost events just described. So the Reuter model gives a static drop of temperature, of air temperature, from sunset to sunrise, but does not take into account any temperature variation due to advection of air and of the physical change of water. The model assumptions are pure radiative nocturnal cooling under clear sky conditions and 0 wind speed. Looking at the formula here, The delta temperature is the lowering of air ground temperature from sunset to a value of time t during the night. Delta time is the time elapsed from sunset to the time t during the night. And d is the decay coefficient obtained from the interpolation of the latter two data. So by looking at the two graphs, it was possible to apply a theoretical model to the case studies, and it well interprets both cases with the appropriate coefficient, the decay coefficient. Finally, a phenological model, the progressive Utah model, was applied in order to estimate the flowering phase of the golden delicious cultivar, namely the central flowering open, like in the picture on the right. Only the central flower is opening at the start of the flowering phase during spring 2004 due to the lack of phenological measurements. So the most important parameter used in the model and which drives the process is the 2-meter hourly air temperature. So looking at the graphs, the bud development is divided into two stages. The chilling accumulation along the solid line during fall, satisfied on December 12, 2003, and satisfying the chilling units requirement. Then along the dashed lines during winter and spring, the heat accumulation satisfied on April 20, 2004, satisfying the growing degree hour requirement. And these two values come from the calibrated data in the study by Rea and Etchell. Then the main results, so the February frost event, when radiative cooling was enhanced by the advection of cold air stream from the north. March frost event, where radiative cooling was weakened by Hora del Garda wind that enhanced the atmospheric mixing inside the canopy. The surface energy budget was driven by latent heat flux on February event due to the presence of dry air and by long wave radiation towards the atmosphere during a March event. Then Reuter model provides a good interpretation of the ground temperature behavior using the decay coefficient, and the growing degree hours requirement was satisfied on April 20. So the blooming phase is expected about 3 weeks after the March frost event just described. So the wind is one of the variables that contribute to modulating a frost event. In February, the north wind enhanced the cooling, while in March, the Hora del Garda wind weakened the cooling. But the radiative cooling is still the most important component. Looking at the apple orchard inside the canopy, the layout, the structure and the size of canopy can change the intensity and the pattern of the parameters. A simple model like the Reuter model is so able to simulate the temperature drop in both frost events. And the application of the progressive Utah model allowed to exclude damages to apple trees during the flowering phase, because the March frost event is 20 days before the start of the flowering phase. So finally, future perspectives with the high resolution weather models that are not sufficient, especially for complex mountain environments like Trentino and Adige Valley. So in order to improve prediction, the downscaling is needed. And for this downscaling, more measurement campaigns like JEPRI project are needed. And then it is very important to use more sophisticated models for correctly predicting the temperature drop before a frost event for crops protection and in order to activate the frost protection system in time. Thank you.
Thank you, Tiziano, for your nice presentation. Now I open the floor to the committee for questions.
Maybe I can start with
Please.
one question. Actually, I have two questions. One concerns the effect of the Oro del Garda, and because you observe a change in relative humidity, but is this the effect of an advection of humidity, of a different humidity from the wind, or is it just an effect of the difference of temperature?
Okay, I turn to the slide here. So the relative humidity was measured in this case 3 meters above ground level, so near the top of the canopy, while wind was measured 6.5 meters above ground level by the sonic anemometer. So there is a difference in height, and I can show you this slide because it contains the wind speed here measured at 3 meters and 6.5 meters, and as you can see at 3 meters above ground level, the black line, the wind is zero, is very weak, while the Oro del Garda present is measured only at the top levels. So there is this wind, the Oro del Garda, flows over an initial stratification layers that is deposited near the ground, and okay, I turn to the relative humidity. Okay, so the relative humidity is quite constant during these 2 hours due to the mix produced by this advection.
Sorry, I didn't understand. So you claim that the humidity remains constant because it is mixing vertically the humidity that is already present?
Yeah, because okay, I change another graphs that I have here, March. Okay, because the relative humidity remain quite constant in the lower layers, and as you can see at 6.5 meter is not constant, but it grows, but of 2, 3, 4, 5% during the same time. So there is a quite a big difference between the two levels.
Okay, and if I can, a second question, if
Yes,
I can ask us. Yes. You showed us the Reuters model and the fit that you can obtain using a coefficient D.
Yes.
But was this coefficient D calibrated on the data, or I mean, were you able to predict its value somehow? So I mean, does this model have some predictive power or not? Because I think that fitting this kind of law on the data is not very surprising. I mean, so
yes, in my case, in these cases, the D coefficient is come from the interpolation of these two data. So it comes from the observation of delta temperature during the cooling in the two frost events. So and the difference in time. So in this case is only an interpolation, but it can be calibrated for a precise frost event in function of the type of frost event with a mathematical computation. But in this case, only represents the relation between temperature and time.
But so the values that you obtain were consistent with this mathematical prediction or not?
I only computed this type of computation, and how can I say? It is quite the behavior is quite good comparing to the behavior of the air ground temperature.
Can I just
Okay,
ask?
thank you.
Can I just ask
Yes.
in between? Did you get the same D for both cases?
No, they are different.
Okay.
For the February frost event is minus 2.3, and for March is larger because the delta temperature is larger. From March, it starts from 13 degrees to 0 degrees, and in February from 4 until to -4. So the delta temperature is larger for the March frost event because there is a large delta temperature from day and the night.
But the question was not about the delta T, it was about the D, the coefficient.
Yeah.
Do you find two different values of the coefficient?
Yes.
Okay.
They are different comparing February and March events. See, the K coefficient is more negative for March frost event.
Mm-hmm. Since I was already asking, I'd like to ask a second question. The first case seemed to have a cumulative latent heat flux that was positive even during the night. How do you explain that when you had? So what's the reason for that?
For the February frost event?
Yes.
Okay, it is positive during the day and during the night because.
Yeah, but why during the night?
Because during the night there is the presence of the foehn wind. It affected to the apple orchard dry air, and still we are during the night there is evaporation during this very dry air, and the day before this frost event there was liquid precipitation, so rain, and the evaporation was enhanced a lot.
Okay, thanks.
Thank you.
Other questions from the other committee members? If not, we should move on because we are very late. So thank you, Tiziano. Thank you. And we kindly ask Selene to put us in the room, and I apologize. Okay, thank you everybody, and welcome back to this first session of graduations in the Master of Science program in Environmental Meteorology, jointly managed by the University of Trento and the University of Innsbruck. We have the pleasure to have here the Rector of the University of Trento, Professor Paolo Collini, and the Vice Rector for Students' Affairs and Teaching of the University of Innsbruck, Professor Bernhard Fügeschuch. We are very happy of having them here representing the two universities that have been involved in this new Master of Science program jointly operated. And I now leave the floor to them for greetings the candidates and for proclaiming them.
Who's the first?
Professor Collini, I guess you are the first.
Okay, thank you. Well, I would say that it's really a pleasure to be here today with you. Unfortunately, not physically together, but still the meaning of the ceremony is the same. And for us, that's something more than just a regular, important, but regular degree awarding ceremony, because this time the first time that we award the degree in our master in meteorology. And the master, when I say our, I mean University of Trento and University of Innsbruck together, in a joint effort of providing a very peculiar and special joint program to a small group of students that have the chance to gear in understanding, exploring, studying, and I hope in the future managing, not the weather, that would be too much, but the way of understanding the weather and helping people in dealing with this aspect of our life that is becoming of a growing importance. The idea of the master that is under the name of Dino Zardi, that is here today with us, was to create a very small but very in-depth program in the area of meteorology. That did not exist at that time in Italy. Still, I believe that we are quite unique in the arena of education in Italy. And of course, we could not do it without the partnership with the University of Innsbruck, because we are in the area of meteorology very strong, but not covering all different issues that we thought were required to provide a master with a broad sense. So I'm very proud because I've been part of this project from the beginning, along with Dino. And remember the first visit to Innsbruck, discussing issues and all the long process that in academia always take to get to something approved. But I'm very convinced that the idea of offering in Italy program meteorology and the idea of doing it with a strong connection with agriculture is a very great point, and I strongly believe that not only for our territory, where agriculture is extremely important, but for the country, this is a very unique program where people can be prepared to face issues in many different areas of activities. So I'm very happy that you are with us today, the first two graduates, and it's one more achievement for my university, and an achievement of which I'm very happy about. So congratulations from my side, congratulations from the University of Trento. I hope they will have some time in the future the opportunity to celebrate, hopefully with something more physical, like a glass of wine or something like that. I'm sure you will do it by yourself, but when you do it, please think about us, that we are with you when you do it. So congratulations.
Thank you.
Thank you.
So I may add on, and it's my turn now, from side of University of Innsbruck, and on behalf of our rector, I also would like very much to congratulate you being the first ones to finalize this new program, which has already been mentioned by Rector Collini. It's a joint study program. We did it together, and I can assure you that it also took some time and efforts from our side, not only from your side, to succeed to finalize, but also to set it up. But it has to be mentioned also that our colleagues, and Georg Meyer is also present today, our colleagues from our Institute of Meteorology, from the very first moment, they were keen to do that because Trento is a very excellent partner. And this is one of the most important things in these partnerships. So as a university, you very often act somehow egoistic. So you look for yourself for the most outcomes, and you look for very excellent, very good partners. And I think this is a very good partnership. I hope you also found out that this program helps you hopefully for your future life. And moreover, I'm very glad that this is another format that we could develop in the Eurasia context, because this is, to my mind, something that the European community is really forced to promote even more, this kind of local situations and understandings of the high potential in these areas in the Eurasias. And another thing is somehow we had a very good flavor of doing the right thing, because you all know very much about these SDGs these days, and I think a program called Environmental Meteorology is on the very first place to be a prominent player in the SDG context, not only SDG 13, where it's about climate action, but I listened to the presentation of Tiziano Tassini, so it's also about food, I just learned. And so I think this is a very good program, high quality, high perspective, and I wish you a bright future with your today awarded grants. Thank you very much.
Thank you.
Thank you.
Thank you very much for your nice words and encouraging ones. So I think we should now proceed to the proclamation of the candidates. Again?
I think I'm the first.
Yes.
We, the Rector of University of Trento and the Vice Rector of University of Innsbruck, on the basis of the unanimous judgment of the examination committee, given the results of your exams and the discussion of your final thesis, by the power of Italian law, we declare Mr. Michele Giurato, Master in Environmental Meteorology. Your final grade is 110 cum laude out of 110. Congratulations.
Thank you very much.
Congratulations, we can clap.
Thank you.
Okay, it's
Professor Fugishu, it's your turn. Thank you.
Yes. We, the Rector of the University of Trento and the Vice Rector of the University of Innsbruck, on the basis of the anonymous judgment of the examination committee, given the results of your exams and the discussion of your final thesis, by the power of Italian law, declare Mr. Tiziano Tassini, Master in Environmental Meteorology. Your final grade is 101 out of 110. Congratulations.
Thank you.
Thank you very much, Professor Fugishu. Just a few words before we leave. It's quite late and we are very sorry about being later than we foreseen. I would like to express my own gratitude to the two rectors for being here and for honoring us with their nice words and with their presence. I would like also to thank the committee who has been working on this session and all the staff that have been preparing it, from the secretaries to the technicians that have been all of this possible. I also would like to express my gratitude to colleagues, both at the University of Trento and at University of Innsbruck, especially colleagues that have been working on this program since the very beginning. I would like to mention Professor Meyer, and I'm happy he's here now, and Professor Matthias Rotach, the director of the Institute of Atmospheric and Cryospheric Sciences. We have been working on this program since 2014, and step by step, we managed to go through many troubles that always arise when you make something new, something very different from what's already existing. But we went through that, and in the end, we managed to have good students, good lecturers. That's quite promising, and as our rectors told us, it's something that we needed to have. We knew in the very beginning that University of Innsbruck had a very long tradition in meteorology, starting from the end of the 19th century. So it was very helpful for us to rely on the availability, the nice availability of these colleagues and all the expertise they put together. And we hope they are as happy as we are today of having this connection, which is quite fruitful. And we also went through this COVID pandemics, I think, quite well, despite all the troubles we had. But students gave us nice feedback of all the courses they have been attending, not only in Trento, but also in Innsbruck. And so the last thought of mine is to the students. We are very happy that they bet on this new course. They decided to start this new course when there was no experience before. So it was quite a challenge for them, but we hope that we have been giving them something useful for their future life, for their future profession. And we are looking forward to new graduates coming up. This late March, we will have other candidates, and the number of students who are applying to the course is increasing. And so we hope that this will be a good initiative for many years to come. So thank you once more to all those who have attended this ceremony. Thanks to the rectors, the authorities, the committees, and hope to see you soon for new graduations. And congratulations again to our new laureates.
Thank you.
Thank you. Bye.
Congratulations again. Thank you to everybody. Thanks a lot.
All the best. Thank you.
Bye. Bye-bye.
Bye.
Goodbye.
Thank you very much, Dino, for being the engine,
Bernard.
the driving force.
Take care.
Thank you very much. Thank you, Georg. It's always a strong support, yours.
Yeah.
Oh, pardon.
Bye. Bye-bye.
Bye-bye.
Bye-bye.